21 small earthquakes recorded beneath a volcano may not sound like much in a region accustomed to seismic activity. Yet when those tremors occur beneath one of the most closely watched volcanoes on Earth, attention follows. Mount Saint Helens has spent decades reminding scientists that volcanic systems can remain active long after their most famous eruptions fade from public memory. The recent recording of 21 earthquakes beneath the volcano has renewed interest in a mountain whose history is defined by repeated cycles of destruction, rebuilding, collapse, and renewal. Is the volcano merely adjusting to the slow movement of magma and underground fluids? Does the cluster of earthquakes represent a routine pulse within an active volcanic system? Or are these tremors evidence that deeper geological processes continue to reshape the mountain from within? The answers remain uncertain, but the geological setting of Mount Saint Helens offers important clues. Far from being a dormant monument frozen in time, the volcano remains an active and evolving feature of the Cascade Volcanic Arc. Its lava dome, built through repeated eruptions and collapses, exists because magma continues to move through the crust beneath southwestern Washington. Every earthquake, every subtle deformation, and every change in volcanic behavior contributes to a broader picture of a volcano that has never truly gone quiet. Mount Saint Helens rises approximately 8,363 feet, or about 2,549 meters, above sea level in southwestern Washington. Located about 96 miles, or roughly 154 kilometers, south of Seattle and about 52 miles, or 84 kilometers, northeast of Portland, Oregon, it occupies a prominent position within the Cascade Volcanic Arc. This chain of volcanoes stretches from northern California through Oregon and Washington into British Columbia, marking one of North America's most active volcanic regions. The existence of Mount Saint Helens is tied directly to a massive tectonic process occurring far beneath the Pacific Northwest. Offshore, the oceanic Juan de Fuca plate is slowly descending beneath the North American plate along the Cascadia subduction zone. As the oceanic plate sinks into the mantle, increasing temperatures and pressures release water trapped within minerals. That water lowers the melting temperature of surrounding rocks, generating magma deep below the surface. Over long periods, this magma rises through weaknesses in the crust. Some magma cools underground, forming intrusive rock bodies. Some reaches the surface, fueling volcanic eruptions. Mount Saint Helens represents one of the locations where this process has repeatedly delivered magma toward the surface over hundreds of thousands of years. Compared with several neighboring Cascade volcanoes, Mount Saint Helens is relatively young. Geological evidence indicates that the modern volcanic system began developing approximately 40,000 years ago. Earlier volcanic centers occupied nearby locations, but the current mountain emerged through successive eruptions that built layers of lava, ash, volcanic debris, and pyroclastic material. Volcanologists classify Mount Saint Helens as a stratovolcano. Such volcanoes form through alternating eruptions of viscous lava and explosive volcanic material. The resulting structure typically consists of steep slopes and complex internal layering. Stratovolcanoes often produce some of the most powerful eruptions on Earth because their magma tends to be rich in silica and dissolved gases. The mountain's geological history reveals repeated episodes of growth and destruction. Large eruptions periodically reshape the volcano, generating extensive ash deposits across the Pacific Northwest. Lava domes formed and collapsed. Portions of the volcanic edifice failed catastrophically, producing landslides and debris avalanches. New volcanic structures emerged atop the remains of older ones. Long before the famous eruption of 1980, Mount Saint Helens had established a reputation as one of the most active volcanoes in the Cascade Range. Native American oral histories describe powerful eruptions and dramatic changes in the mountain's appearance. Geological deposits confirm numerous eruptive periods during the past several thousand years. The mountain's activity accelerated significantly during the centuries leading up to European settlement. Several eruptive episodes occurred between approximately the late 15th century and the mid-19th century. These eruptions produced lava flows, ash clouds, pyroclastic flows, and dome-building events that reshaped the summit region. By the late 19th century, however, Visible volcanic activity had largely ceased. Decades passed without major eruptions. Forests expanded across volcanic deposits. To many observers, the mountain appeared dormant. That perception changed dramatically during the spring of 1980. A series of earthquakes began beneath Mount Saint Helens during March of that year. These tremors marked the movement of magma upward through the crust. Soon afterward, steam explosions blasted a crater into the summit area. Scientists observed swelling on the volcano's northern flank as magma accumulated beneath the surface. The deformation became increasingly pronounced. Measurements revealed that part of the volcano was bulging outward at astonishing rates. The north flank continued expanding throughout April and early May, indicating that pressure was building within the mountain. On the morning of May 18, 1980, a magnitude 5.1 earthquake triggered the collapse of the unstable northern flank. The resulting landslide remains the largest documented debris avalanche in recorded history. Approximately 2.5 cubic kilometers, or nearly 3 billion cubic yards, of rock and debris raced downslope. The sudden removal of overlying material allowed pressurized magma and volcanic gases to expand explosively. A lateral blast erupted northward with devastating force. Forests were flattened across hundreds of square miles. Ash rose tens of thousands of feet into the atmosphere. Pyroclastic flows swept across the landscape. Rivers became choked with sediment and debris. The eruption transformed the volcano's appearance. The symmetrical summit disappeared, replaced by a massive horseshoe-shaped crater open toward the north. Elevation was reduced by more than 1,300 feet, or approximately 400 meters. Yet the eruption did not end the volcano's story. In many respects, it marked the beginning of a new chapter. Following the 1980 eruption, magma continued reaching the surface. Between 1980 and 1986, a series of dome-building eruptions occurred within the newly formed crater. Thick, viscous lava accumulated near the vent rather than flowing great distances. As new lava emerged, it stacked upon earlier deposits, gradually constructing a lava dome. Lava domes differ significantly from fluid lava flows associated with volcanoes, such as those in Hawaii. The magma at Mount Saint Helens contains higher silica content and greater viscosity. Instead of flowing easily, it tends to pile up near the eruption site. The resulting structures often resemble giant mounds or spines of fractured rock. The lava dome within Mount Saint Helens crater grew through repeated extrusion events. Portions collapsed periodically, generating rockfalls and pyroclastic flows. New magma continued pushing upward, enlarging the dome over time. Another major dome-building phase began during 2004. Activity resumed after nearly 2 decades of relative quiet. Fresh lava emerged within the crater and continued accumulating until 2008. This eruption differed from the spectacular explosions of 1980. Instead, it involved the slow extrusion of thick lava. Giant rock spines emerged from the dome. Blocks fractured and crumbled as magma pushed upward from below. Over time, millions of cubic yards of new material accumulated inside the crater. The result was a complex dome occupying much of the crater floor. Although less dramatic than explosive eruptions, these processes demonstrated that the volcano remained active and capable of transporting magma toward the surface. That history explains why recent earthquake activity attracts attention. The recording of 21 earthquakes beneath Mount Saint Helens does not automatically indicate that an eruption is imminent. Small earthquake swarms occur periodically beneath active volcanoes worldwide. In many cases, they reflect adjustments within the volcanic system rather than the approach of a major eruption. Several processes can generate volcanic earthquakes. One possibility involves magma movement. As magma migrates through fractures and conduits, surrounding rocks may crack under stress, producing detectable seismic signals. Even small amounts of movement can generate earthquake clusters. Another possibility involves hydrothermal fluids. Hot water and volcanic gases circulate through fractures beneath the volcano. Changes in pressure can trigger earthquakes as fluids move through underground pathways. Tectonic stresses also contribute. the crust surrounding Mount Saint Helens experiences regional deformation associated with broader plate interactions. Existing faults can respond to changing stresses, generating small earthquakes unrelated to immediate eruptive activity. Because of these possibilities, volcanologists examine earthquake swarms alongside other monitoring data. Ground deformation, gas emissions, thermal anomalies, and changes in volcanic seismicity all contribute to understanding volcanic behavior. A cluster of 21 tremors therefore represents a data point rather than a definitive warning. Nevertheless, such activity confirms an important reality. Mount Saint Helens remains an active volcanic system. The volcano contains a complex network of magma reservoirs, fractures, hydrothermal zones, and conduits extending through the crust. Even during periods without visible eruptions, geological processes continue beneath the surface. Understanding those processes requires examining the structure of the volcano itself. The crater created during 1980 measures roughly 1½ miles, or about 2½ kilometers across. Within this crater sits the lava dome, surrounded by steep crater walls and volcanic deposits accumulated over decades. The dome is composed primarily of dacite, a volcanic rock containing relatively high silica content. Dacitic magma tends to be thick and sticky compared with basaltic magma. This viscosity influences eruption style by trapping volcanic gases within the magma. As pressure builds, gas-rich magma can produce explosive eruptions. Alternatively, if gas escapes gradually, lava may emerge more quietly, constructing domes and spines. The interior of the dome contains fractured rock, cooling lava, and remnants of previous extrusion episodes. Beneath the dome lies a system of conduits that once delivered magma from deeper reservoirs. Those reservoirs remain a subject of ongoing scientific study. Geophysical investigations suggest that magma exists beneath Mount Saint Helens at multiple depths. Rather than a single large chamber, the volcanic plumbing system likely consists of interconnected zones where magma accumulates temporarily before migrating upward. These reservoirs evolve continuously. Magma cools, crystallizes, mixes with newer magma, and interacts with surrounding rocks. Pressure conditions change over time. Fluids circulate through fractures. Earthquakes provide clues about these hidden processes. Modern monitoring technology allows scientists to observe such activity with remarkable precision. Networks of seismometers detect tiny earthquakes that would otherwise go unnoticed. Global positioning system instruments measure ground movement with centimeter-level accuracy. Satellite radar can identify subtle surface deformation across large areas. Gas monitoring systems track emissions from vents and fumaroles. Together, these tools create a detailed picture of volcanic behavior. At Mount Saint Helens, monitoring efforts intensified after 1980 and remain among the most comprehensive for any volcano in the United States. The volcano serves as both a natural laboratory and a significant volcanic hazard. Its position within the Cascade Range places it near populated regions of Washington and Oregon. Transportation corridors, rivers, reservoirs, and communities lie within areas potentially affected by future eruptions. The nature of future activity remains uncertain because volcanic systems rarely follow predictable schedules. Mount Saint Helens has demonstrated a remarkable range of eruptive behavior. It has produced explosive eruptions, lava flows, dome-building events, ash emissions, pyroclastic flows, and massive landslides. Different eruptions have varied significantly in scale and style. The volcano's geological record indicates alternating periods of intense activity and relative quiet. These cycles can last years, decades, or centuries. Consequently, even modest earthquake swarms receive close attention. The recent 21 tremors may represent nothing more than routine background activity within an active volcanic system. Similar swarms have occurred before without leading directly to eruptions. On the other hand, earthquake clusters sometimes accompany changes in subsurface conditions. The significance lies less in the absolute number of earthquakes and more in their characteristics. Depth, location, magnitude, timing, and relationship to other monitoring data all influence interpretation. Scientists seek patterns rather than isolated events. If earthquakes migrate upward through the crust, that may indicate magma movement. If ground deformation increases simultaneously, confidence in that interpretation grows. Elevated gas emissions can provide additional evidence. Conversely, earthquakes without supporting changes may simply reflect ongoing volcanic adjustment. For now, the tremors highlight the continuing dynamism of Mount Saint Helens, rather than signaling a specific outcome. Geologically, the volcano remains exactly what it has been for thousands of years, an active stratovolcano fueled by subduction-driven magmatism. Its lava dome serves as visible proof of that activity. The dome exists because magma reached the surface repeatedly during recent decades. Every block of dacite within the structure records a chapter in the volcano's continuing evolution. Even during periods of apparent calm, internal forces remain at work. Heat continues rising from deeper levels of the crust. Magma reservoirs slowly evolve. Fractures adjust to changing stresses. Hydrothermal systems circulate hot fluids through volcanic rock. Small earthquakes punctuate these processes, providing glimpses into an otherwise hidden world. The broader geological context reinforces the importance of continued observation. Mount Saint Helens is not an isolated feature, but part of an active volcanic arc extending hundreds of miles along western North America. Numerous cascade volcanoes, including Mount Rainier, Mount Adams, Mount Hood, and Mount Shasta, share the same tectonic origin. Each volcano responds differently to the supply of magma generated by subduction. Some remain relatively quiet for centuries. Others experience more frequent activity. Mount Saint Helens has historically ranked among the most active. Its behavior during coming years will depend on processes occurring far beneath the surface, beyond direct observation. Monitoring networks will continue tracking earthquakes, deformation, gas emissions, and other indicators. Every new data point contributes to understanding a system that remains in constant motion. For now, the 21 recorded tremors serve as a reminder rather than a prediction. They remind us that Mount Saint Helens remains geologically alive. The lava dome occupying the crater is not merely a remnant of past eruptions, but part of an evolving volcanic structure. The mountain's history is one of repeated transformation, driven by the movement of magma generated deep within the Cascadia subduction system. Decades after the eruption that reshaped the volcano and captured global attention, Mount Saint Helens continues to change. The crater, the dome, the underground plumbing system, and the surrounding landscape remain products of ongoing geological forces. Small earthquakes reveal those forces at work, even when no eruption is visible. Whether the recent seismic activity ultimately proves insignificant or becomes part of a longer-term pattern remains unknown. What is certain is that Mount Saint Helens remains one of North America's most closely watched volcanoes, a mountain whose geology continues to evolve through the same processes that built it thousands of years ago. The 21 tremors are another entry in that continuing record, evidence that deep beneath the crater and lava dome, the volcanic engine that created Mount Saint Helens has not stopped operating. Another factor that makes Mount Saint Helens especially significant is its tendency to rebuild itself after major eruptive episodes. Many volcanoes experience explosive eruptions, but few have been observed reconstructing large portions of their summit area in such detail. The lava dome inside the crater stands as one of the clearest examples of that rebuilding process. Rather than remaining a static pile of rock, the dome reflects an ongoing cycle of magma supply, extrusion, cooling, fracturing, and gradual modification. Geologists often describe volcanoes as living geological systems because they evolve continuously over time. Mount Saint Helens illustrates that concept exceptionally well. The mountain visible today is dramatically different from the volcano that existed before May of 1980. The crater, the dome, the altered drainage systems, and the extensive volcanic deposits surrounding the mountain all testify to the speed with which volcanic landscapes can change. The presence of recent seismic activity also highlights the importance of distinguishing between dormant and extinct volcanoes. Mount Saint Helens is not extinct. An extinct volcano is generally considered one that no longer possesses an active magma source capable of generating future eruptions. Mount Saint Helens does not fit that description. The tectonic mechanism responsible for creating magma beneath the Cascade Range remains active today. As long as the Juan de Fuca plate continues descending beneath the North American plate, magma generation will continue somewhere within the volcanic arc. That ongoing magma production is why even relatively small earthquake swarms are carefully cataloged and analyzed. Earthquakes provide one of the few direct windows into processes occurring several miles beneath the surface. A seismic signal may reveal the opening of a fracture, the movement of magma, the circulation of hydrothermal fluids, or the adjustment of rock under changing pressure conditions. Individually, such events may be minor. Collectively, they help reveal the state of the volcanic system. Mount Saint Helens also occupies a unique position in modern volcanology because few volcanoes have been monitored so extensively throughout an eruption cycle. Scientists have observed periods of unrest, explosive eruptions, dome growth, long intervals of quiet activity, and renewed magma extrusion, all within the span of several decades. This record has provided valuable insights into the behavior of stratovolcanoes worldwide. The 21 recorded tremors therefore carry importance beyond their immediate location. They add another set of observations to a long-term dataset documenting the volcano's evolution. Whether the swarm proves to be a brief episode or part of a broader trend, it contributes to understanding how Mount Saint Helens functions as a dynamic geological system. For now, the volcano continues to stand as a reminder that geological time does not operate according to human schedules. Years of calm can coexist with active processes deep underground. The lava dome remains in place within the crater, but it was built by magma that rose long after the mountain's most famous eruption. The recent tremors suggest that the same forces responsible for constructing that dome are still present. Mount Saint Helens may appear quiet from a distance, yet its geological story remains unfinished, shaped continuously by the tectonic forces that created the Cascade Range and continue to influence the Pacific Northwest today.